Hello everyone, let's analyze. So today we're going to talk about the arithmetic of integrals as well as improper integrals in multiple dimensions, and then we'll begin to discuss computation of integrals. How, once we know that an integral exists, how do we actually compute it? So let's begin with the arithmetic. Suppose A is a bounded subset of Rn, alpha is some number, and that both functions f and g mapping a to r are both bounded and Riemann integrable over a. Then the function f plus g is Riemann integrable, and the integral can be distributed to the sum. So the integral of f plus g is the integral of f plus the integral of g. The scaling of f by alpha is Riemann integrable, and the integral of the scaling is the scaling of the integral. If f is less than or equal to g for all x in the domain, then the integral of f is less than or equal to the integral of g over the domain A. And we also get the result that the absolute value of the function f is Riemann integrable, and the integral of the absolute value is an upper bound for the absolute value of the integral of f. And if A has volume and f is bounded by m, which of course we're assuming that f is bounded, for all x in A, then the absolute value of the integral of f is less than or equal to the max value of f, or m, times the volume of A. So this arithmetic of integrals should look familiar to you. You saw a very similar set of results, at least results I believe 1 through 4, already proven when we talked about integration on the real line. In fact, the proof for the results 1 through 4 we've proven on the real line, and the proofs remain the same. Rather than dealing with interval partitions, we have rectangular partitions, but the ideas are precisely the same. So I would encourage you to review the proofs for the results 1 through 4 on the real line and adapt it to rectangles from lecture 2. Now for result 5, since f is bounded above by m, then the absolute value of f as a function of x is less than or equal to m times chi a. In other words, where x is inside of a, then I get the absolute value of f is just less than or equal to m, which is of course our assumption. And for x outside of a, the absolute value of f of x we're assuming to be extended is just 0, which of course is equal to m times 0 for x not in A. Now since A has volume, chi A is integrable. And since the absolute value is also integrable, we have from result 4 that the absolute value of the integral is less than or equal to the integral of the absolute value. And from result 3, we have that the absolute value of f is less than or equal to m times chi a. Since m is a scalar from result 2, that scalar can be factored out. And of course the integral of chi a over a is the definition of the volume of A, and we have our result. So the mean value theorem for integrals. If f maps a subset of Rn to R is continuous, and A has volume is compact, remember compact means closed and bounded, and the domain A is connected, then there is an x naught in A for which the integral of f over A equals f at that point times the volume of A. Another way of putting this is that there is an x naught in A for which f of x naught equals the average of f over A, where the average is the integral of f divided by the volume of A, supposing, of course, that the volume is not 0. So let's prove the statement. Now, since f is continuous on A and A is compact, we know that f achieves a minimum and a maximum. Since f of x is bounded below by f at the min and bounded above by f at the maximum, then for all x in A, using the arithmetic of integrals we've developed, f of x min times the volume of A, right, which you could think of as the integral of chi A over A, is less than or equal to the integral of f over A, which is less than or equal to the maximum value times the volume of A, which again, the volume of A is just the integral over A of chi A, the characteristic function of A. Dividing all three terms by the volume of A, again, supposing the volume of A is not 0, gives us this inequality. Right? F at its minimum is less than or equal to the average of f over A, which is less than or equal to f at its maximum. So then, applying the intermediate value theorem yields that there is an x naught in A equal to that average value. Or, to put it into this language, the integral of f over A equals f evaluated at some point in A times the volume of A. And we've proven our result with an asterisk. Well, what if the volume of A is equal to 0? In fact, that's why the theorem statement is written this way and is not written this way, because perhaps the volume of A is 0, which means this statement would not be defined. So could we prove this if the volume of A is not 0? Well, that case will be left as a scavenging exercise to the reader, in the sense that I claim we've already proven that result when the volume of A is 0, and I'll leave it to you to go find it. Now, let A and B be bounded subsets of Rn, and suppose F is defined on the union of A and B. Now, if the intersection has measure 0, and F is integrable over A, B, and the intersection, then F is integrable on the union of A and B. And furthermore, the integral of F over the union of A and B equals the integral of F over A plus the integral of f over b. Right? We don't have to consider the integral of f over the intersection. Right? Hopefully you see why that's the case, because the intersection has measure 0. So far, all of the results we're discussing should be familiar to you. We might, as we progress through this proof, imagine that perhaps A and B are some rectangles in Rn that share a face, for example. Or we could picture R2, right, and A and B are two squares or rectangles that share an edge. So let's split f up into the pieces where we know it's integrable. That is, we'll let fa be f times the characteristic function of a. Right? That means fa agrees with f when x is in a, but otherwise is 0. Similarly, fb agrees with f if x is in b, but otherwise is 0. And fa intersect b agrees with f if x is in a and b, but otherwise is 0. Now, each of these functions are integrable by assumption Therefore, the integral of FA over the union is just the integral of f over a, because this function is 0 outside of a. Similarly, the integral of fb over the union is just the integral of f over b, and the integral of f intersect a and b over the union is just the integral of f over the intersection. And again, we should know already precisely what value this term has. Now I can reconstruct f from these individual parts. Now I can't just say f equals fa plus fb, because where a and b intersect, then I'm counting f twice. So I need to subtract one of them. So I get f is equal to fa plus fb minus f at the intersection. That way I don't count twice all the x's that are in the intersection. From that we would obtain that the integral of f over the union is equal to the integral of fa plus fb minus f over the intersection, all evaluated over the union. Right, just using the arithmetic of integration that we just got through developing. Well, remember, fa is f times chi a, fb is f times chi b, and fa intersect b is f times chi intersect b. And as we just got through saying, this is the integral of f over a plus the integral of f over b minus the integral of f over the intersection. But the intersection has measure 0. And we know from our bounty of integral theorems that if f is integrable, its integral over a set of measure 0 is 0. So we have our result. So in all our discussions, a has been bounded and f has been bounded. So let's briefly discuss improper integrals. Okay, so now let's suppose that our domain A is a subset of Rn, but not necessarily bounded. And we'll let A map A to R, we'll let F be bounded and non-negative. Suppose that f is integrable over the n-dimensional cube that's negative a to a by negative a to a by negative a to a n times. So the n-dimensional cube, where each edge rather, is length 2a. Now we're going to suppose that f is integrable over this cube for any length side. In other words, for all a greater than or equal to 0. But then if I take the limit as a goes to infinity, and I actually get a limit, I get a finite number, then we call that number the integral of f over a. This definition should look familiar to you. In fact, if we replace n with 1, which is to say to remove n, that n there, then we have already seen precisely this definition when discussing improper integrals on R. So this is just the n-dimensional analog. Now, of course, just as we've discussed before when discussing improper integrals on R, do we need the cube to grow symmetrically? Is it important to have symmetry as we allow the domain to grow unboundedly? No, we don't need symmetry actually. We just need something to grow unboundedly, that's all. Assume that f is non-negative and bounded and integrable on every cube. Then f is integrable over a if and only if the following condition holds. For every sequence of bounded sets bk that grow monotonically, now what do I mean that the sets grow monotonically? I mean that the next one contains the previous. and for which the sets grow arbitrarily large. Now, what do I mean that these bounded sets in Rn grow arbitrarily large? I mean, if I take k large enough, I can fit any cube. So if I have such a sequence of bounded sets, and the limit as k goes to infinity of the integral of f over bk exists and is finite, then that limit equals the integral of f over a. So again, we've actually seen this result where instead of bounded sets in Rn, bk, we had intervals bk and r that contained any symmetric interval negative a to a. We've seen the theorem before, but then we didn't prove it. So let's take the opportunity to prove it now. Suppose f is integrable and bk is a sequence of subsets as described. They grow monotonically in size and without bound. In other words, any cube can be fit into one of the sequence of subsets. Our goal is to show that the limit as k goes to infinity of bk of f exists and is equal to the integral of f. So we're proving the forward direction of our proof. The fact that f is integrable over a implies, by definition, that the limit as a approaches infinity of f over the cube exists and equals the integral, which is some finite number. Well, since we're dealing with the limit, we'll have to break out our epsilon. For any epsilon, there exists a m greater than or equal to 0, such that the integral of f over a minus the integral of f over the cube, negative m to m to the nth power, is less than epsilon. And in fact, if I were to take a larger than m, I would still get the same less than epsilon result. That if I were to replace this m with a little a greater than m. But we just need one cube, so we'll use this one, which we're guaranteed to exist by the definition of what it means to have a limit as a goes to infinity. Now, keep in mind, we actually don't need these absolute value lines, and I'll explain why. Since f is non-negative, the integral of f over the cube, negative a to the nth power, is an increasing function of a. In other words, as the cube gets bigger, since f is non-negative, I'm either not adding anything to the integral, or I'm adding something positive to the integral. So we see that this integral is an increasing function of a. And of course, it's bounded above by the integral, right? You can't get past that. Similarly, because bk is a growing subset, a sequence of subsets, the integral of f over bk is an increasing sequence, or we could say an increasing function of natural numbers k, and it also has the same upper bound. Also, the fact that these subsets bk grow without bound means that I can choose a capital K large enough to contain the cube negative m to m to the nth power. So for all little k bigger than or equal to big K, I get that the integral of f over the, I'll call this the m cube, is less than or equal to the integral of f over bk, because bk is a bigger set. It has more of the positiveness of f if f is positive outside of this cube. And if f isn't, well then I would just get equality if f is just uniformly 0 outside of the cube, or the extension of f rather. And of course, since these sets get bigger, if little k is bigger than big K, I get that this integral is even bigger. And of course, it's bounded above by the actual integral of f over its domain. Right? Remember, anytime we have some of these domains getting bigger than A or not intersecting with A in some parts, we're dealing with the extension of F. So I know already if I were to take this last term and subtract this first term, one, I'm going to get something positive, which is why I don't need these absolute value signs here, but also I get something less than epsilon. So if I subtract this term from this term, I get something positive, but also something less than if I subtract this term from this term. And that would be less than if I were to subtract this term from this first term, right? The integral of f over minus the integral of f over the m cube, and we've already established that that's less than epsilon. So it follows that the integral of f over a minus the integral of f over b little k is less than epsilon for all little k greater than big K. Well, that's the definition of a convergent sequence. So that limit exists. It's finite because it's equal to the integral of f over a, which we assumed to exist. Right? That was our initial supposition. So we've proven the forward direction. Let's prove the backward direction. Suppose now that the limit of f over these growing subsets bk exists and is finite, and so we'll call that limit L. Our goal now is to show that the limit as a goes to infinity, where a is the half the side of the edge of these cubes, I need to show that that integral exists, or that the limit of those integrals exist. So let a be positive. Because bk grows without bound, there's a k that will contain my a cube. And because this a cube is contained in bk, the integral of f over the a cube is less than or equal to the integral of f over bk, which is less than or equal to L, because L is the limit of this as k goes to infinity and bk grows with k. As we stated before, since f is non-negative, the integral of f over the a cube is an increasing function of a, and as we just pointed out, it's bounded above by L. Therefore, that limit as a goes to infinity exists because I have an increasing function bounded above. Therefore, it has a finite limit. Well, if that limit exists and is finite, then that's the definition of f being integrable over a. And when it exists and is finite, the integral of f over a is equal to that limit. So we've proven our result. So we understand when a function is integrable. How do we actually go about computing an integral over a? Now, of course, we know that, well, we could take the infimum of all upper sums, the supremum of all lower sums, make sure they match, and then, of course, that's the integral, but, well, that seems excessive. Surely there's a more practical way to do it. In fact, we know there's a practical way to do it because you've been doing it ever since, well, Calculus 3. Let's begin with rectangular domains. Rectangular domains in R2 specifically because, well, things are simpler then. Let's build our intuition of why things work there, and over the next few lectures we'll build up. So Fubinis Theorem says let R be a rectangle in 2 dimensions, A to B by C to D. Then if F is continuous, that's a typo, this should be on R. So if F is continuous on R, then the integral of F over R is the integral from a to b of f of x y dx. In other words, I'm going to keep y constant and just integrate with respect to x. That'll give me a function of just y, and then I integrate that function with respect to y from c to d. Now I could also integrate with respect to y first and then with respect to x, so long as f is continuous. Now if all we know is that f is integrable on a, not necessarily we have continuity, again that should be r. And for each x naught in AB, the function f of x naught y is integrable. Then we can compute the integral of f over r by integrating with respect to y first and then integrating with respect to x. Similarly, if f of x comma y naught is integrable for each y naught in my interval, then I should integrate with respect to x first and then with respect to y, and that will give me my integral of f over the rectangle. So we'll prove the statement. Now, we're just going to prove one of the statements. In fact, we're going to prove this one. Because if I were to just replace my x's with y's, I would get this statement. So the arithmetic for this one and this one, or the proof or the logic for this one and this one would be the same. And of course, if both of these are true, then if f is continuous, it satisfies both of these conditions simultaneously, and we get this result. So this first bullet really follows from the second bullet. So let's prove the second bullet point. So we'll let g as a function be a function of x. G is going to map a to b to r, be defined by g of x is equal to the integral from c to d of f of x comma y dy. So if I take f and integrate with respect to y for each x, then I'll get a function of x, and I'm calling that g. Our goal is to show that g is integrable over the interval a to b, and that the integral of g from a to b is the integral of f over the rectangle. So we have our goal before us. So you might imagine that we're going to partition the interval a to b. We'll partition the interval c to d. And of course, from these partitions, we can construct a partition of the rectangle R by just taking the partitions in X by the partitions in Y. So, if I take my lower sum of F over the partition of R, right, well, by definition, I get the sum of the infimum of F over these subrectangles times the volume of the subrectangles. What is the volume of the subrectangles? Well, it's just the length of one side times the length of the other. Of course, the length of a side is the one-dimensional volume. Now, note that the infimum of f over the entire rectangle has to be less than or equal to the infimum of f on just a strip of y for each x. In other words, if I were to isolate x and only let y vary from one edge of the partition to the next edge of the partition, then whatever the infimum there on that fixed x, right, has to be greater than or equal to the infimum of f if I let f vary over the entire subrectangle. Therefore, right, now I'm going to investigate this sum right here, but I'm going to disregard this part. So if I were to remove this part, I get this sum here. And using this inequality, I can replace this term with this term, and I would get this less than or equal to. Now here I have the infimum of fx times the volume, or the length of the partition in y. Well, that is the lower sum of fx over a partition of c to d, which means it's less than or equal to the integral of fx over c to d, which we're assuming exists. And that's equal to g of x. That's actually the definition of g of x, is let x be held constant and integrate with respect to y. That gives me g of x. And this is true for all x. Right? G of x is a particular number, and this particular number is bigger than this. Right? Now if I multiply this and this by this term we left off, right, then I can get an upper bound for that. Of course, since this inequality is true for all g of x, it's true for the infimum of g in each subpartition of the interval a to b. So therefore we have the lower sum of f over a partition of p, right? So that's where we started. We know that this times this is less than this from our previous page, right? And then of course this term is in common. Well, that's actually the definition of the lower sum of g over a partition of a to b. Right? That's exactly what that means. So we could apply the same type of analysis to the upper sum and get that the upper sum of g over a partition of a to b is less than or equal to the upper sum of f over a partition of the rectangle. So let's put all of that together. Right, we have an upper bound of our lower sum of f over a partition of the rectangle, and we have an upper bound, we have a lower bound of our upper sum of f over a partition of the rectangle. And specifically sandwiched in the middle is the lower and upper sums of g over a partition a to b. Right, so these are sandwiched in the middle. But remember that f is integrable over r. That's our assumption. Which means I can find a partition that'll make the difference between the upper sum of f and the lower sum of f less than epsilon. So I can find a partition of a to b, a partition of c to d, and a resulting partition of r, for which the difference of the upper sum and lower sum is less than epsilon. Right, just by definition of what it means to be integrable. And because my upper and lower sum for g is sandwiched in the middle, the difference between my upper sum and lower sum of g for that same partition on a to b is also less than epsilon. So it follows that g is integrable over a to b. Furthermore, the integral of g, and remember this is the integral of g, from a to b equals the integral of f over the rectangle R. Because it's sandwiched in the middle, these are arbitrarily close, but this is also arbitrarily close. So they must be, if this equals this, or rather if the infimum of this equals the supremum of this, the same goes for g, and so we get this result. And of course a similar dance with logic would show that if we were to swap all our x's with y's, we'd get that second result of the second bullet point. So a corollary is, well, what if I don't have a rectangle? Right? What if my domain is not so nice? For example, let's consider the domain that's sandwiched here between psi of x and phi of x. So suppose psi and phi are both continuous functions of a to b, and in this case we get 0 to 2 pi, but from a to b. Suppose f is continuous in this sandwich space. Then to integrate f over the space is to integrate f of xy with respect to y from psi of x to phi of x. Right? So for each x, if I were to hold x constant, this would be a number, this would be a number, this would be a number. I would just have a function of y. I integrate with respect to y for each x, right? Gives me a function of x. I integrate that with respect to x, and I have f over this space. By the way, it just so happens that psi and phi in this picture meet at the endpoints, but they don't necessarily have to. Right? It could have been that there's a vertical edge on the right and a vertical edge on the left. Now let R be a rectangle containing A. How do I know such a rectangle exists? Well, remember, phi and psi are continuous on the closed interval a to b, so they're bounded. So let's extend f to our rectangle in our typical way. F and f tilde agree for x and a, and f tilde is 0 in the rectangle but not in A. Now notice that the boundary of A, right, is, well, it's the graph of phi, that would give me the bottom. It's the graph of psi, that would give me the top. And then it's all values on the left between psi of A and phi of A. That's the left. And of course, for my picture, the left was just a point, but it could have been a line, a vertical line. And the right, which also could be a vertical line, but again, in my picture, happened to be just a single point because psi of B and phi of B equaled each other. Now, since A1, A2, A3, and A4 each have measure 0, the boundary of A has measure 0. It follows that the set of discontinuities of f tilde also has measure 0. Therefore, f tilde is integrable over R. Furthermore, for each x between A and B, fx tilde that maps C to D to R, right? In other words, if I were to fix x and let y vary vertically, okay, that is my fx of y tilde. And it's continuous except, well, except for where it intersects phi and where it intersects psi. There it may not be continuous. But if it's only discontinuous at 2 points, well, then it's integrable. And remember that I'm integrating f tilde over the interval C to D, but remember that f tilde, once I get below phi and above psi, is 0. That's why if I, sorry, I can't get this to highlight the way I want. Right, this integral from C to D, right, for each fixed x is not going to go past psi at the top and phi at the bottom because f tilde is 0 below phi and 0 above psi. And that's how I get my result. Well, that's all for today.